In this video, we're going to discuss Reimann sums. And it's my opinion, really, that if you understand Reimann sums, then it's going to help you a great deal, especially, for instance, in my engineering classes. When I teach engineering, we get to a certain section in it, and I have found a distinct difference between the students who understand Reimann sums and those who don't, as far as how to conceptualize some of the things that we're doing. So often I'll stop and give a brief overview of Riemann sums at that point, because truly it makes a difference. I actually think it makes a difference in the math, instead of just blindly doing definite integrals, which is what we're going to do in the next video. If you understand what the definite integral is asking you to do, it makes life so much easier, and we can all stand a little bit of life being a little easier instead of, oh my gosh, what are we doing? All right, so hang in there and just try to understand the concept behind here, paying attention to which things talk about width, which ones talk about height. This isn't making sense right at this second, but you'll catch on. So pay attention to the little tiny details, right? And get the overall picture, and then I'll have you do a problem, on your own. Next video will be definite integrals. All right. So what the concept here is, we're going to try to find the area underneath the curve, is in this case between the curve and the x-axis. All right. And so the way I introduce it is I start off with something very simple. And this happens to be the y is equal to 3x line, which is sort of a member of the curve family. Okay. So here's my y is equal to 3x, and you can see these little boxes that I drew underneath here. And I'm interested, for some reason, okay, but for the purposes of this video, we're interested in the section between 0 and 4. And I'm going to try to find the area underneath there. Now, some of y'all are probably going, okay, really? Hi, we can compute the area of this underneath this triangle right now using geometry, right? So let's try that for just a second. So the area for a triangle is 1/2 the base times height, right? So 1/2. We can see that the base for this triangular shape is 4. And the height would be this value right here. And since I have an equation for y, and I know that this x is 4, then I can just compute that the height is 3 times 4. Normally we would just say 12, but bear with me for a minute. So this is 1/2 times 4 times 12, right? Which turns out to be 24. So this is 24 square units, right? Now we know that, right, from geometry. This is not a big surprise. So what we're going to hold on to here is that the area of this is actually 24. All right. Now, what we would like to be able to do is to compute the area of really not geometrically friendly shapes. All right. So we might want to, say, be able to find the area between something that's like this. And we want to find, say, this area right here plus this area, and there's no nice geometry formulas for that. So then became the quest for how can we do that using calculus and limits. We're back to limits. All right. So we're going to start off. This is really kind of slow. Hang in there, listen to the terminology, because you're going to hear this again. So, and again, as we move through here, and then when we get to definite integrals, then you're going to hear the terminology in a different way. All right. But I'll try to show you the bridge over to the next video. So let's start off easy, and let's make the math as easy as we can. All right. So I'm going to arbitrarily divide this triangular section into 4 subintervals. So they call this a partition. This entire setting up this concept and the area, and then dividing it into little intervals is called a partition. We're going to partition on, this area under the curve, right? Now, in some books they call them subintervals, and in some they call them just intervals, right? So I'll probably switch back and forth so that you can hear both the terminologies. And we're going to use rectangles, right? Because I can fit a rectangle in any shape. It's fairly easy to do the math. I don't even need a 1/2, right? I just need the base times the height. So we're going to use rectangles. It'll make more sense here later, all right? And if I divide it into 4 sections, I would have this where I end at 4. I would say, all right, I'm going to end at 4. So if we go from 0 to 4, I'm going to go 4 minus 0 over 4, which makes each interval 1. Now, you're like, I can divide 4 into 4 equal parts and say it's 1 without having to go through this 4 minus 0 over 4. But if this is A and this is B, then B minus A over how many intervals do you want turns out to be the width. Okay, so if you had something like, I want to look between 1.2 and 7.95, and you're like, okay, so you would go 7.95 minus 1.92, I think is what I said, over however many intervals you want. So yes, when the math is pretty straightforward and lovely numbers and integers, you can figure it out in your head. But if not, what you're going to do, because this always works, is you go, where do I want to end? It is B. Okay, so you're going to start at some x value A, go over to some x value B, divide by however many intervals you want. Now, this is like I said, we have a partition. This is going to be the width of each subinterval or interval that you're going to create. If you make them all the same width, right, then it makes the math easier. You could actually make some, if you had something like this, you can make some really wide and some really thin and some wider, and then come back and put another in there. But if they're different widths, it makes the math so much harder. The largest width is called the norm and is sometimes designated as this. Okay, we'll talk more about this as we go. So the norm is the largest width interval. And if they're all the same widths, then they call that a regular partition. Okay, so we are going to deal with what's called a regular partition because the math's easier. Okay, there's nothing wrong with the math when the intervals are different widths. It just makes life harder. All right, so let's just stick with the concept of a regular partition. All right, and let's do some math with this. Now, you would draw this line right here, technically, because that's where we're going to end up. Each partition is going to be 1 unit wide. So you would have another partition, if I could draw a straight line, it goes down through here, another one through here, another one through here, and this one. So these are our 1, 2, 3, 4 partitions, right? Now, once you get the partitions set up, you have a choice. Do you want to use a left endpoint, a right endpoint, or a midpoint? So if you use a left endpoint, you would look at this. Let's look at this first partition right here. So we're going to look at this partition right there. And the point to the left, which is right here, the x to the left, is going to be used to calculate your height. Well, what's the y value right here? It's 0. So this partition actually contributes nothing to the area because you go straight over to the next interval. Then for the second interval, you would look at this x, which is on the left, and you would draw over to the next interval. Then you would use the left endpoint, draw over to the next one, left endpoint, draw over to the next one. And so that takes care of my 3 endpoints. If you did a right endpoint, you would have, here's your intervals like this. Right. You would go to the right and draw toward the left, and go to the right of this interval, draw to the left. Go to the right of this interval, draw to the left. Draw to the right, go to the right of this interval, and draw to the left. Now you see how in this case the right interval gave us too much green area. It extends past the triangle. Over here, the leftmost left a bunch of empty spaces, and so we would have just these. I'm going to straighten these up while I'm here. Sections, right? You could also use midpoint, which requires you to calculate the midpoint, but it actually gives a really nice kind of first impression of the area. And the reason is because it's kind of a little over and under. So if you have your intervals, which I couldn't draw them to be equal, you would find let's look at interval 1. You would find the midpoint of interval 1, which is right here, and you would draw both directions. Find the midpoint of interval 2, find its y, draw both directions. Midpoint of interval 3, find its y, draw both directions. Midpoint of interval 4, find its y, draw both directions. Okay? Now, since the one that seems to confuse my students the most is the one that has no contribution right here, we're going to do a left endpoint just to practice. Keep in mind, the reason is because sometimes people think that if you use a left endpoint, it always undercuts the area, okay, that it leaves too much open places, and a right one always overshoots the area. But that's not true. It depends on the slope, depends on factors like that. So don't get that into your head that left is always under and right is always over. Okay? Now, so we do know just from the figure that I'm probably using the little rectangular area approach. I'm going to be a little bit under my known value of 24. Okay, but what we're going to do is try to fill out this table. Some of your books have you do these going sideways, which I think doesn't lend too well to understanding what's going on. So here's what we're going to do. Let's say that we have been assigned this y is equal to 3x function, and we've been asked to find the Riemann sum for this function between 0 and 4. And we want to use 4 subintervals or intervals, depending on what you call it. So this is A, this is B, and so you're going to go B minus A over however many intervals you want. So in our case, it would be 4 minus 0 over 4. So each interval is going to have a width of 1. So when you do this rectangular area thing, the area for a rectangle is the base times the height. And this would be your base, and this would be your height, correct? Going up and down is your height. All right, so the base is the width of your subinterval, and this is actually delta x. Okay, so the width side to side is delta x, delta being the change in x, okay, distance over an x. And in our case, we're going to do a regular partition, so each one's going to be the same width. You okay with that? All right. Now, when I divide it into 4 intervals right here, and I'm going to use a left endpoint version, then I use each x on the left of each interval. So let's go back over here. All right, so this is 0, 1, 2, 3, 4, right, on the number line, not how many intervals. This is not talking about how many intervals. This is just the numbers on the number line, like this would be 5, 6, 7, 8. Okay, so I use the X on the left in each interval because this is a left endpoint version. So the X on the left, okay, we would have 0, 1, 2, 3, 4, which is where we're trying to get to, actually becomes the beginning of the next interval, which we don't care about. So the left ones are 0, 1, 2, 3. So we'd go 0, 1, 2, 3. 4, again, is the beginning of the next interval because it would be to the left of the next interval, which is outside my 0 to 4 interested section. Okay? Now then I'm going to compute f of x. So I would have 3 times 0 is 0. 3 times 1 is 3. 3 times 2 is 6. 3 times 3 is 9. Correct? Then what we're going to do is compute the area, which is the base times the height. And this, okay, we have the base times the height. And the base is delta x. And the height is f of x, right? For each of the little rectangles in my section. So here's my f of x. Here's my delta x. So it's going to actually be 1 times 0, 1 times 3, 1 times 6, 1 times 9. Now, you don't have to show all these steps, but I'm trying to show you the pattern, okay? So this is going to be 0, 3, 6, 9. And then we're going to take the sum of these little baby rectangles, okay? So the sum of the area, remember this sigma notation from algebra class, okay? The sum, okay, so this is sigma. It stands for let's sum them up or add them up. So this is going to be 18. And so, yeah, we're not even close to 24. All right. So, but do you see how much empty space we had underneath that triangle? So I'm not surprised it's, kind of relatively low, but it seems a little bit more lower than I was expecting, but okay, I'm not too terribly surprised. Okay. Now, the concept behind Riemann sums is that the smaller you make the width, okay, of each little interval or subinterval, the more accurate your answer is going to get. So that if we, doubled these up, then maybe we could get a better answer, a more accurate answer. All right, so here we go. So here's what it looks like if we're going to have 8 subintervals. Okay, so this was 4. This is 8. So if we wanted, let's do the math. Okay, so b minus a over 8, because we're going to go from 0 to 4 again. So this would be 4 minus 0 over 8. So each width is going to be a half. That's the base. That's your delta x, right? And do you see, if you can just compare these two, do you see how going from 4 intervals to 8 intervals, there's a lot less empty space, right? So I should be getting closer to 24, right? Likewise, if you look over here, this is a right end point, and do you see how it's a better estimation than 4 because there's not so much extending past that triangular area, and it works better for the midpoint version, right? But again, we're going to stick with the left, all right? Now, so here we go. So I think I should be closer to 24, okay, than I was before. We're going to use the left endpoint of each interval. And each interval is going to have a width of 1/2. And the 1/2 width is how wide your base is. Remember, we're doing rectangles, so it's the base times the height, right? So each one of these is a half. All right. So when you can figure that out and just string it down, it works pretty well. All right. So then we're sticking with y is equal to 3x. And we're going to figure out what our left x's from each interval is. Well, we're going to start with 0. And then it's a half a unit wide. So the next left point is a half. Then we go a half over, so that's 1, and then another half, and then a half, and then another half, and then a half. And I've lost part of my little table, so we're going to put the next one down here. Now, if you put 7 halves and then the next one would be 4, you don't go all the way to 4 because using a left endpoint, 4 is the left endpoint for the next interval outside of my 0 to 4. Okay, so we're just going to extend this down to 7 halves. Sorry about that. All right, and here we go. So f of x is 3 times 0 is 0. 3 times a half is 3 halves. 3 times 1 is 3. 3 times 3 halves is 9 halves. 3 times 2 is 6. 3 times 5 halves is 15 halves. And 3 times 3 is 9. And 3 times 7 halves is 21 halves. Okay. Now the area is your base times your height. Remember, this base is your delta x. This is your f of x is your height. So when you multiply these out, right, so you're going to go 0 times a half is 0. 3 halves times 1 half is 3/4. 3 times a half is 3 halves. 9 halves times a half is 9/4. 6 times a half is 3. 15 halves times a half is 15/4. And 9 times a half is 9 halves. And 21 halves times a half is 21/4. Okay? And when we do the sum of the areas, we get 21. Now that's definitely closer to 24, and I'm not too surprised because there's not too much empty space. All right? Sometimes, like I said, your books or your teachers or whatever will demonstrate this by saying the sum of the areas is, and they will put the delta x times something that looks like f of x1, or they may call it c1, f of x2 plus f of x3 plus, f of your last one, right? Let's just say last for this second. I'm not going to deal with some of the other stuff right now. But to me, this sideways thing, okay, yeah. Okay, now that I see how it looks like as a table, I could probably do that. But at first blush, this is not really necessarily the way I would catch on to it really quickly. If you do, well, good. All right, now this is what it looks like if we got it to 50 intervals. I'm not going to make you do 50 intervals in a table. But you see how I can just barely see, can you see there's just barely see some little open spaces there? Here you can't really, you can kind of see these little tick marks where it's going over and under. And this is where it's going over. It's really pretty close, right? And this is what it looks like. I thought you'd want to see. This is what it looks like if you have 100. So here's n is 100. I had the Desmos to draw these. All right. So there's n is 100. Okay. So let's rehearse for just a second. Okay. A is the beginning of the partition that you're interested in. B is the end, right? Dividing by n is how much the width is. Okay. So for each partition or each subinterval in the partition, this is delta x. right? Okay. Now, as you can tell, we're really trying, it would be great if we could get the number of intervals to be huge, okay? 100 looks almost like it's big enough, okay? But we're trying to make it get larger and larger and larger. Okay, so as you try to draw something and make it bigger and bigger and bigger as you verge along, okay, is this sounding anything like a limit? So we could approach this one of two ways, really. We could say we want the limit as the width, and they'll call it the norm, and it'll look like this. Approaches 0. So if you make the width approach 0, so you're making it thinner and thinner and thinner, you can pack more of the intervals in there. If you had something that was not a regular partition, and like I showed you earlier, you had like here's a large one, then we had some smaller ones, different sizes, and then we had excuse me, let's say this is slightly larger. So this is my largest one. This is slightly larger. All right. If we use this norm concept, okay, remember that the norm is the width of the biggest subinterval, then we would drive this one down to 0. So we would collapse it. Okay, so this wall is going to come in, and this one's going to collapse down to as close to 0 as we can get it. That would then make this one the next biggest. It would come to the top as the biggest interval, right? So then this norm, this one, is the norm, okay, the new norm, and it would collapse to 0. So this one would collapse to 0, giving us maybe a new norm right here. And then that norm is going to collapse. So if you use the concept of the norm is going to collapse to 0, the biggest one's going to collapse to 0, approach 0, as close as we can get to without getting there, then we're going to have an infinite number of rectangles in there, right? So the other thing they'll talk about is that, n's going to go off to infinity. So trying to approach an infinite number of rectangles, trying to approach an infinite number of rectangles would make them have to be microscopically thin as they approach 0, right? It's any way you want to look at it. Now, this area concept works great until if you have something like this, where it goes above and below the x-axis. So here's your x-axis right here. So this would have a positive area. This would be a positive area because your y values are positive, right? So if f of x, the y value, is positive, then you're going to have a positive area. Let me write that out instead of just using the plus sign. Okay? If your f of x, though, is negative, see how it drops down here? These would be negative values. So you're going to get a negative Riemann sum, or if you're looking at areas, you would get a negative area. If you add them together, you sort of get the difference between the positive areas and the negative areas, like a net, kind of like a net area because they cancel each other out. If you are truly wanting to find the area, like you're going to cover it with carpet or something, these two right here that are already positive are great. And for this one, you would have to change the sign. So you're going to take the negative of the Riemann sum negative. So the negative of a negative, it's going to be positive. And this one is going to require you to do the negative of the negative Riemann sum, and you would get a positive. Now, this, I'm just sort of throwing that out there for you to think about. This will be something we talk about in the next video, which is the definite integral. All right. But I just want you to kind of think about that. Now, what we have been doing in one of the versions of the formal definition of this looks like this. Try to say it to you. All right, so this is the sum. Okay, remember this is the summation. This is the sum of f of whatever c is, c of I, times delta x of I, right? So this is your width that we've been dealing with, which is your base, right? This is your y value that we were working with, and this, excuse me, is your height, right? This is the number of intervals that you want. So it's saying start with the first interval and go to however many intervals you need. This is saying the C that you're going to use, and C is, are you using a left endpoint, a right endpoint, or a midpoint, has to be bounded between the previous interval and the next interval, right? It can't be way over there. So C is, are you using a left endpoint, which is that one, a right endpoint, or are you going to find a midpoint where you would actually add the two together and divide by 2? Now, if you do this, let's talk about a different variation of this. All right. So this is what we just talked about, right? This part right here. We just talked about that. You have n intervals. This is your these are your y values for the heights of your rectangles. This is the width, which can be a regular partition, and they could all be the same width, or it could be different values, okay, of your sub or intervals of your partition. This is the norm, which is the largest width interval in your partition, and we're going to make it approach 0. So we're going to make the largest one approach 0, and then the next largest one approaches 0, and then the next largest one approaches 0. So we're going to start collapsing all these intervals down so I can get it as close to an infinite number of intervals as I can get in there, okay? And they're going to set up a definition and say this is the definite interval, because the difference between an indefinite interval, which we went over, and a definite integral are these limits right here. So this is a lower limit. This is an upper limit of integration, right? Excuse me. But these A's and B's are exactly what we were dealing with before. So if I had wanted to go from 0 to 4, right, this would be A, this would be B. All right. Now, this, when they start going from kind of like a measurable, this is my opinion, okay, or my view of it. If you're going from a measurable distance in x, which is delta x, and then you make it this really tiny, I sometimes say infinitely small, but that's actually not, they're opposite of each other, but I'm going to try to make it as small as possible so it's becoming smaller, 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 smaller as it goes to 0. It's not really something you could put a ruler down and measure it at this point. So it changes to d of x. So d of x to me is just a microscopically thin delta x. Okay, so it takes the place of the delta x, right? And this function of x, remember how when we were setting these up in the table, and I went through where I went 3 times this and 3 times that and 3 times this, because I actually wanted you to insert it into the function. That's what this is. This is your function, okay? So for us, it would look like I want to go from 0 to 4. My function was y is equal to 3x, and this is dx. Now, for something that's going to come up later, and the thing that upsets my engineering students sometimes is this is an awful little tiny thing, right? I mean, it's supposed to be microscopically thin. You would think it would be kind of barely noticeable, but it drives everything. Okay, so sooner or later in your life, okay, down the road, they're going to have these mixed up variables and functions or whatever, where maybe you would have a y here, right? From 0 to 4 of y dx. And you're going, great, I've got a y and a dx. And the same thing, I don't really want to deal with y and dx. So this one wins in the tussle between, do we go all y's or do we go all x's? The dx wins, right? The dx is the controlling variable. So the dx says everybody has to be an x, and you go, well, oh yeah, okay, y is 3x, so let's put 3x right there. And if dx is going to win, and this one has to be an x, these also have to be x numbers. You can't use y numbers. These have to be x numbers. So everybody has to be an x. So dx, which is such a tiny little thing, is the absolute controlling factor. Now, let's try what we did before. And I'm going to give you a preview of the next video. All right. So forget the 0 to 4 for a second. If I had asked you to do the indefinite integral, right, of the 3x, you would go, oh, okay. So it's 3, right? Add 1 to the power, divide by the new power, right? And then you would have gone plus c, right? Because we have a family function because it's indefinite. This one is definite, which means it's kind of a definite thing. It's like right in your face. So a definite is slightly different. You don't do the plus c. You say, I'm going to evaluate it from 0 to 4. And they typically have this little straight line that represents evaluated from, okay, and we're going to go from 0 to 4. Okay, now the way you do that is you take this 3/2 x squared and you put the 4 in first. So you put 4 squared. So this goes in and then you subtract. You always subtract. It's always, always, always a subtraction. And you would go 3/2 0 squared. Okay, so this one goes in where x is. It's always a subtraction in between. All right, so let's see what we've got. Well, 3/2 times 16 minus 3/2 times 0. Well, 0 times anything is 0. 2 goes into 16 8 times, right? And 3 times 8 is 24. So see how that gets you exactly the 24 we started out with? So this is the lead-in to a definite integral. Looks like this. But I want you to understand that no matter how crazy it looks, all right, if they said I want to go from -2 to 4 of x squared plus 3x plus 2 dx, all right, this is your base. This is your height. This is your left endpoint, and this is your right endpoint, lower to upper, right? Of a bunch of little baby, teensy tiny little rectangles shoved in between this curve and the x-axis, where you are, in effect, calculating an area. And that, I think that's really important for you to understand. And it will help you in your physics class, your engineering classes, and so forth like that. It really helps you to understand what this is computing. This is literally computing the area is the base times the height for a whole ton of rectangles, okay, to come up with the area for a complex curve. It's great. I mean, the hair on your arm should be standing up. All right. So there'll be a link to the next video down in the description as usual. If you're going to need more help on remembering how to do indefinite integrals, I'll try to put that in there as well. But, just back up through the previous links and stuff like that. And then I'll see you at the definite integral video.